So this is our picture, and this is the problem we're trying to do. So I'm going to start this from here again. I asked the students to think about this question. We have this system here. We're trying to figure out, first of all, if this mass little m moves down the ramp 20 centimeters, how far does the wedge move to the right? And what's going to happen is, as I said, the length of string between this point and this point is fixed, because once the wedge hits the wall, this distance of string will still be there. The distance between this point and this point is fixed in terms of the string length, because you can see that that's just a fixed length of string right there. It's not going to get shorter because the pulleys are mounted on the wall, right? That means that the pieces of string that are not fixed in terms of length would be, we'll go to like the blue one and just make it red or something, just as a different color. The distances that are not fixed would be basically this distance here can get shorter, and this distance here can get shorter, right? All of those distances can get shorter, basically this one and this one. And you'll notice that the length here to here and the length here to here is fixed as well, right? So what I would say that's going to happen is that if the wedge, for example, were to move, if this block moves down 20 centimeters, I would say that basically this length of string and this length of string both have to get shorter at the same time. Does that make sense to you guys? As this one moves down to like some position here, and the string comes this way, the entire wedge will have moved, and I'm going to undo what I did because I don't want to, the entire wedge will have moved, like, let's say to here. If the wedge is like right here, for example, then the block is now going to be somewhere like down here, and it will have moved this distance, while the wedge will have moved basically some length of string here got shorter on this side, and it got shorter on this side as well. So I would say that the answer would be 10 centimeters to the right. I'll stop for a second. Does that make sense to you guys? Does anyone have any questions? Basically, you have to pull string from here and from here. And I'm going to clean all the stuff that I did real quick here now. So we still have our same diagram that we can work with. Doesn't want to undo any farther, so we'll just erase these. So now that we know that, we know something important about what's going on in this problem. We know that, I don't think it will even erase the other stuff, so I can pretty safely just, okay. We now know that the acceleration of this block down the ramp, let's use red, the acceleration of block M is going to be pointing this direction, down the ramp. But it's going to move at twice the acceleration. So it's going to move at 2a down the ramp. Twice the acceleration, because for every meter that this one moves, the wedge, the block moves twice as far. So you get double the acceleration, similar to what happened in the last problem. The key thing here that's very different is that these accelerations represent different things. So first of all, the acceleration A represents the acceleration, I would say, of the wedge relative to the ground. Okay, and I'm going to just call that AWG. Okay, and it's basically going to be equal to A to the right. Okay, it's a vector, it's A to the right. The acceleration 2A is equal to the acceleration of the block relative to the wedge. We're going to call that one A block wedge. And this one is, I need to move over just a little bit here. Okay, so this one right here is the accelerate, it's equal to 2A down the ramp. Or along the edge of the wedge. But there's another thing that we need to calculate here, which is what would be the acceleration of the block relative to the ground. Right? That's the next thing we want to calculate then. what is the acceleration of the block relative to the ground? All right. Can anyone tell me how you would find that? Exactly. This one plus this one should be equal to this one. That's related to our relative acceleration equation. So that's the first thing we're going to talk about here. The reality is that block M is not just moving down the ramp. It's also attached to the wedge, right? So block M actually has two accelerations. It's got an acceleration to the right that's A, and it has an acceleration downward that's 2A. And the sum of these two vectors is going to give you the total acceleration of block M. In an equation, we would say basically that the acceleration of the block relative to the ground should be equal to the acceleration of, and this is where our relative velocity equation comes in handy, the block relative to some third thing, which in this case is the wedge, plus the acceleration of that third thing, the wedge, relative to the ground, the sum of these two. And so what do these vectors look like? Well, one of the vectors, and I could actually probably use a shape here for this one of the vectors is directly down along the ramp like that, right? So the acceleration of the block relative to the wedge is this vector that goes down this way. It's actually kind of the right angle even. And it has, of course it changed right the last second. It has a magnitude that's 2A in that direction. And the acceleration of the wedge relative to the ground, right, is a vector that goes, let's use the vector arrow again. Shapes, arrow. Shapes, arrow. And we'll just move it. No. Okay, we can tilt it. Nope. Can we tilt it? Can do it with a mouse. Go mouse this way, something kind of like that. That's probably fine. So then this one has a magnitude that's A, right here. And then if we take another vector, the sum of these two vectors is going to give us the what we're looking for. We want to do shapes, arrow, and let's use blue or something for this. The vector that goes between here and here, nope. Shapes, arrow, shapes. That vector is going to be your acceleration of the block relative to the ground. That vector there. And in order to find the length of it, we'll do our normal vector component addition. So in reality, what block M does in this system is it kind of moves along a line like this. It moves diagonal and down to the right like this. Whoops, I clicked my button by accident. Yeah, basically M moves along a line. No, stop doing that. Why is it doing it? Oh no. Okay. M is going to move along a line that's going to go kind of down like that, basically. Is that, can you guys visualize that? But it's moving kind of along a path like this. It's going to the right and diagonally down this way. Okay. So we got this information, right? And what we could maybe even do here, yeah, we're gonna have to do it later, but I was thinking we could actually sum these accelerations right now, but we'll do that here in a little bit. Because we also need to draw forces acting on these objects. Okay, so I might actually draw the forces, no, I can't draw them on this picture, it's gonna look too weird. But I might erase this stuff right here, now that we've said what it is, and use it as a place to start drawing our free body diagrams. So let's do that real quick. Just delete this. And say that we want to draw free body diagrams for each of these objects. So I guess what I would like for you guys to do is maybe do that yourself right now. And I'll stop recording for a moment. That's going to make 2 videos though. Maybe we'll just keep recording. I'll give you guys a minute. Can you try to draw the free body diagram for each of these objects, the mass and the wedge? So try to draw each of those real quick. Just do it on your own piece of paper. label all the forces. And I'm going to tell you that on mass n there's 3, and on mass form I think there's 5. Treat the forces down here as one normal force. Okay, hopefully you guys have gotten some of these forces written on here. I'm going to try to start drawing them on the screen now. So the little block M, it's going to have 3 forces. It's going to have a tension. We'll use red for the forces. So there's going to be a tension. It's going to be pointing back up the ramp like this. It's not going to let me... Oh, that's too bad. Maybe because of where I'm starting it. Okay, we're just going to draw these without using the arrows then. We're just going to draw them in by hand. Should look just fine, I hope. So our vectors for the forces on M, you're going to have a force that's going to go straight back this way. Okay, that's going to be... Oh, I've got ink to shape on. Okay, so you've got a force that goes back that way. That's going to be our tension force. You're going to be a force that's going to point perpendicular to the surface. That's going to be the normal force. This normal force is basically the force of the wedge on the block, right? There's also going to be a weight that's going to go straight down. Okay. We've got our accelerations over here that we'll put on this picture too. So our we may do that. We'll do that in a second, actually. We'll come back to that. For 4M over here, can you tell me what the forces acting on this one are? And again, if you saw the stream last night already, like, don't answer, but what are the forces that are acting on the wedge going to be? Can someone like Hugh or Mike can tell me what they are if they're confident? Okay, why are there 2 tensions? There's going to be a tension here, right, T? And then let's go back to the right just a little bit. Nope. There's going to be a tension here. Oops, yep, there's going to be a tension here. In fact, I like drawing these forces on this guy anyway. There's going to be a tension there. Okay, so there's those 2, right? So over here I'm just going to label those 2 as, it's on the edge of the screen, so this is really hard to write with now, but basically there's going to be a 2T force going this way. And then you're also going to have your obvious like things like weight, right? So there's going to be a 4mg. There's going to be some kind of a normal force with the ground, right? Ng. There's going to be the reaction force from the block here, right? There's going to be the force this way that's N. Another N. And there's going to be a tension. This is the weird one for this one, and this also shows up in your homework. There's also going to be a tension force like this. So there's going to be 2 T's on this pulley. Those tensions are going to act on this guy right here. So ultimately what we end up with is we're going to have a tension force. I'm going to scooch over here so I don't have to write on the edge of my tablet. You're going to have a tension force that starts from here, but it's going to go down to the right. That's going to be T. You're going to have the weight of the object, which is going to be 4mg. Oh my god, why is this so hard? Let's undo that one. That one just looked really bad. I want to try to draw at least somewhat straight line. Oh no. There's your 4mg. And then there's a normal force. This normal force here has to react back on the wedge too. And the normal force from the ground goes straight up. That looks okay-ish. Those are all the forces acting on the wedge and all the forces acting on the block M. Do you guys have any questions about that? All right, in that case, let's start talking about how we want to solve this. We're going to start with this one first because it's a little easier to handle, and then we'll deal with this guy separately because we almost need another board to even explain what's happening with it. So our acceleration on our system here is this way. Whoa, I don't want to use that marker, my bad. This one's fine. The acceleration for the wedge, we said, was to the right. It has an acceleration that we're calling A. So what should I do with my coordinate system for this one? How should I orient my coordinate system for 4M? Yeah. And why would that be? Yep. So we want one that goes basically like that, right? This would be our x direction, and this is going to be our y direction, because we want the acceleration to be only along this axis if we can, because if we make the acceleration of the wedge point, and again I need to be doing this to the mouse, if we make the acceleration of the wedge point in the same direction as the x-axis, then it makes it so that the y acceleration is 0. So when we write down our equation for this object, and now let's try to do that, this angle right here, if we look back at our picture, is the angle that we defined as theta earlier. That angle is going to be the same as this angle here. Hopefully you guys can see that. So right here we've got this angle right here is going to be theta. So it also means that if I extend my coordinate system on the left-hand side here, so our coordinate system is going to extend off this way. If this is theta, then this is 90 minus theta. That means that this is also theta right here. And I think that's all we need, because then we can state that for this system here, if I want to write down what my Newton's second law equation is going to be, it's going to be, go over to the right again. So my Newton's second law equation for the wedge, in the x direction, we can say net force acting in the x direction is going to be equal to the mass, which in this case is 4m, multiplied by the acceleration. And the forces we have in the x direction are going to be 2t plus, right here we have t times the sine of theta, and then we have mg doesn't have a component this way. We have n cos theta, so minus n times the cosine of theta is equal to 0. Nope, not equal to 0. It's equal to 4ma. Can you put all your forces over here? You put your accelerations over here. So this is one of our equations here then that we're going to use to solve this problem. In fact, we can just call that equation number 1 if we want to, so we can refer to it later. The other equation we would get if we really wanted to write it down would be net force acting in the y direction. This should be equal to 0. We aligned our acceleration along the x direction, so that means, I need to go down just a little bit here. In the y direction, if we make up positive, we're going to have the ground force pointing up, so the normal force with the ground, minus the component of n, which is going to be n times the sine of theta, and then minus 4mg is equal to 0. Oh, there's another one. The t multiplied by the cosine theta, so minus t cos theta. There we go. Okay, this equation we're not going to use, but this one we will. So does anyone have any sorry, we're not using this one. We will be using the one that I boxed in. Does anyone have any questions about how I got that equation right there? Where these like sines and cosines came from? I can show on the picture. Nope. Okay, let's go back and talk about the block then. So this guy is complicated because of this situation here, right? And what I'm going to do is I'm just going to copy this piece. Oops. Here. I'm going to copy this. And drag it up here to this picture. Unfortunately, those lines aren't exactly the same direction. It's probably fine. Can I still interact with this? I tilt it up one. That actually looks parallel now. Does that look parallel to you guys? Okay, good. So now what we need to do is to figure out how we're going to do axes for this kind of monster right here. Do you guys want to take a minute and think about how you would do your axes on this one? This is way harder now, because now we have these double accelerations. We haven't seen this before. Why don't you guys just take a moment to think about how would you do your accelerations in this problem? Sorry, not your accelerations, but how would you do your axes? And the hint I'll give you is that while it would be possible to align your axes along this direction here, it is going to be a lot of work. So what I'm going to say is that you're going to have to choose axes in this situation that such that you are going to have some y component of your acceleration and you are going to have your x component of acceleration. You choose how you want to do it. It's either going to be y acceleration up and x acceleration to the right, or something else. Maybe even y acceleration down, actually. So think about it. How would you orient your axes given this problem? And take a minute to think about it. Oh, I now understand what you were saying. Actually, you were saying that we could move to another voice channel and they couldn't follow. That would have been a good solution. Yep. Okay, so what did you guys come up with? What do you think? How do you orient your coordinates in this situation? hmm That's what I would do as well. So what I'm going to do now then is, if that's what we want to do, if we want to take our coordinate system and we want to make it so that, and I'll just like draw the way it's going to be. This one, what thickness is this? Okay, so I'm going to say that we're going to make it so that this direction, so it's moving, it's going down and to the right, right? So we want to have positive x is going to point this way, and we're going to say positive y is going to point this way. And then that means that we're going to have to break up our accelerations into components, right? So we're literally going to have to break up this acceleration into components, which means we need to know something about what the angles are here. So what I'm going to do is we're going to drop another little line right here. Ooh, what just happened? What was that mark? There we go. So we're going to drop shapes, line. We're going to go line from here. Ooh, why did it do that? Maybe I just draw it. Getting these lines in here sometimes is way too hard. So we can use black is fine, I guess. So we're going to have to break up this one into one that goes this way and one that goes this way. Now, we know that this angle here is theta, right? So now what's going to happen is that I believe this angle here is going to be theta. And how can I show that to you guys? So this acceleration basically points to the right. Here, I have to draw it on the picture, don't I? That acceleration A right there, on our diagram, it would be this way, right? It's not a force, but that's the direction it would point. Which means that this angle here, indicate with the mouse, this angle right here, I would say is 90 minus theta. That angle right there needs to be 90 minus theta. Because it's basically the same angle here. Can you guys see that? They don't look like the same angle, but they are. And they should be if the hikes into this line properly. That angle and that angle are the same. So that little blue angle is 90 minus theta, which means that this angle up here has to be theta, because this is a right angle here. That makes sense to you guys? Convince yourself of it on your paper if you need to. Okay, and now what I'm going to do is I'm going to erase that extra line I drew on the diagram because I don't really want that to be there. Okay, it's not a force. We don't want the accelerations being on this diagram. They need to be separate. So now what we do is we say, all right, well, if I look at this system and I know what my x and my y directions are, then my acceleration in the x direction, I would say, is equal to now. If this is A right here, in fact, I can move where that A is located just because it's a little bit clear what's going on here. So if this vector is A, then this vector here would be what? What would this vector here be equal to? That's right. And then this vector here is going to be A times the cosine of theta. So in the x direction, we have 2a plus a sine theta. So I'm going to say it's 2a plus a sine theta. And then the x in the y direction, ay, is just going to be that vector right there, which I said was a cos theta. And now we can do things with this. Does that make sense to you guys? That figure there? Okay. So now what we need to do is apply Newton's second law. And Newton's second law states that the net force acting in the x direction, if you add up all the forces, should be equal to the mass of the object, which is m, multiplied by the acceleration in the x direction. The other equation, of course, is going to be net force in the y direction, equal to the same thing in the y direction, m times ay. Mass is a scalar, doesn't have components. Now the forces that we'll write down here are going to be the forces acting in the x direction, right? We said that this was theta, so I would say that we can break up our force mg into a component that would point down the ramp like this, down the ramp like that, and a component that would point like this, right? That's how we're going to break up mg. You know what? Let's clean this up just a little bit. We can move that right here. And then we can say that mg ends up getting broken down into a vector that goes parallel to what we call the x-axis, and then a vector that here that's parallel to what we call the y-axis. This component should be mg times the sine of theta. This component should be mg times the cosine of theta. So in the x direction, right here, what we're going to get is, since we're taking down positive, because that's the direction it's moving, we're going to get mg cos theta minus t equals m. And then ax is this guy right here, right? So it's times and in the y direction, we're going to have n minus mg sine theta. I'll write that one over here. So in the y direction, here, let's just move this over just a little bit. So in the y direction, we're going to have our force. I can scroll up just a little bit here so we can see it. It's this force N right here. So we have N minus this component, mg sine theta, mg equal to m times ay. So here's our accelerations. Let's block these in because we're going to need to distinguish them. So n minus mg sine theta is going to be equal to may, which is m times a. This looks so bad. So it's m a cos theta. What I'm going to do is I'm going to box all these equations in here. We're going to call this one 2. We'll box this one in. We're going to call this one 3. Those 3 equations we're going to use to solve the problem. We'll do that on kind of a different space. Do you guys have any questions? Go back to where you can see everything. Kind of like that, I guess. Can I zoom out? Here we go. You guys have any questions? Please ask. I know that this stuff is very complicated. You guys have a lab manual problem? 2 of them. They're extremely similar to this. So if there's anything you don't understand yet, like, please ask. I know this is extremely complicated. And I also know that the interface that we're using to show this isn't ideal. Any questions? Yeah. You can think about it as superposition. You could also think about it as, relative acceleration. That's how I introduced it. But if you want to think about these 2 accelerations as just summing together to give you that one, that's fine too. Yeah. Yep. Do you guys have other questions? I think what I'll do now is just move these down to a separate space so we can combine them all together. So there's that one. There's that one. And then there's this one. Those are the equations we want to solve. And the way I numbered these was that basically this was 1. We called this one 1. We called this one 2. We called this one 3. Those are the 3 equations that we want to merge together now. And we'll just do a different color here, just to make it not look so monotone, like dark blue or something. Those are the 3 equations we want to move together. And the way in which we're going to do this is we're going to use what's called the elimination method, which is the method I like to use a lot with these type of problems, and also just in general using Newton's second law problems when you have unknowns that show up in each thing. And so that's what we're going to do. So what I'm going to do is I'm going to kind of take this equation here. I want to use a thicker pen too, so this shows up better. So let's look at what we have, but I'm going to stack them together so you can kind of see what's going on. So I'm also going to do some substituting. So this one I'm going to rewrite like this. mg cos theta, this is equation 2. mg cos theta minus t, and I'm going to just change this one a little bit. We're going to pull the a's on the outside. So it's going to be ma multiplied by 2 plus sine of theta. I'll now write this one here. So equation 3, just might leave some room here. How much room do I need? So n minus, leave some space there, is equal to and then equation 1. I'm going to factor the t out of here. This one is t times 2 plus sine theta minus those are our equations. So here's what we have to do. We need to eliminate t, and we need to eliminate n. And one thing you might notice is that the n here has a minus sign, and this one's positive. I need to use the mouse for this. The n here has a minus sign, and the n here is positive. The t here has a minus sign, and the t here is positive, right? So what I want to do is I want to figure out something I can multiply equation 2 by. So when I add to equation 1, it eliminates the t. Can anyone tell me what I should multiply by? If I want to multiply equation 1 by something so that when I add equation number 2 and 1 together, I eliminate this term right here. What would I need to multiply the first equation by? Yep, so that's what we're going to do, and I'll do this in a different color. We'll go to like green or something like this light green color. So we're going to take both sides of this equation, and we're going to multiply by 2 plus sine theta. So this side and this side over here. The second equation, we need to multiply this n times something so that when I add equation 3 plus equation 1, that I eliminate this term, n cos theta. What do I need to do then to do that? What do I need to multiply equation 3 by so that if I add it to equation 1, I can eliminate the cosine theta. Sorry, I can eliminate n cos theta over here. What should I multiply? Yep, so I need to multiply this side by cos theta. And I need to multiply. This same method, by the way, can be used to solve the problems that you guys are going to be doing, and it will vastly simplify the algebra. I promise you that if you try to isolate t and then solve, you're gonna have a bad time. So last equation, we're not multiplying by anything. So now we need to go to the right so we can actually see what these things are being equal to. Do I really have enough space for that? Probably not. Let's just do it below it. Yeah, let's just do it below. So now what we get when we do this is, let's go back to this blue pen. So now equation 2 is now going to become 2 plus sine theta times this. So that's going to be, you're going to get a, 2 times mg cos theta plus minus, I'll just leave t times 2 plus sine of theta equals ma, and this is going to be this times this, which we can multiply out. So 2 times 2 is 4. 2 times sine theta is going to be 2 sine theta, but you're going to get 2 of those terms, so you get plus 4 sine theta, right? Because you get 2 times sine theta and then sine theta times 2, and then plus the outer terms sine and sine, so you get sine squared. Equation 3 is now going to become n cos theta minus mg sine theta cos theta equals ma times cosine squared. And then the last equation, equation 1, it stayed the same, right? So it's still just, I'll write it right here, t times 2 plus sine theta. And then we have a negative in cos theta, so I'm going to write that one right here. Negative in cos theta. This actually stacked up pretty well. So plus this is equal to, like, things lined up for how I want them to line up. Okay. That's equation 1. Scrolling down just a little bit here. Okay, can everybody see the step from this line down to this line here? And I could probably demarcate it so it's easier to see for people later on if I put like a orange thing or something like this between these. Oh, that just looks ugly. I'll just do a little line here. Can you guys see everything, like how I went from here to here? And more importantly, do you guys notice any mistakes that I made? Okay. So now what we do is we are going to sum these. Why don't you guys take a second to do it yourself? What happens if I add together all of these equations? Okay, this equation plus this equation plus this equation. What do you get on the next line right here? You guys tell me what you get. Okay, we'll take a minute. I'll let you guys do it. Sum them all up, see what you get. Okay, so hopefully you noticed that a bunch of terms cancel, right? This mg cosine theta here, what's up? Someone want to say something? That one cancels with that one. This is beautiful. To me, this is beautiful. I love algebra. This one cancels with this one. This one cancels with this one. Everything cancels out on the left-hand side except for one thing. All you have left over is basically 2mg cosine theta is equal to, and now on this side, you notice that every term has an MA in it, right? So I'm just going to just sum them up. Did anyone sum them all up? What do you get here? What shows up here? Can anyone tell me? What do you get when I add that plus that plus that? What do I get? That's the right answer, yeah. Let's show how we get that. So 4 plus 4 sine theta here plus sine squared theta. Everything is multiplied by MA, right? So this term is just sine squared theta MA. This is cosine squared theta, so you add this one in here, cosine squared theta. Beautiful identity showing up right there, and then plus 4 right here. So what you end up getting then, of course, is exactly what, I didn't know who it was that said that, but exactly these two add together to 1. Just indicate that with like this. Oops. This is 1, right? So 4 plus 1 plus 4 is 9. Plus, and this is the only term left over, 4 sine theta. And then you'll also probably notice that these cancel. Yep. And so we get a final answer for the acceleration. That is A equals divided by this. And that is our final answer. Actually, we can turn it into a number here in a second, because we also know that theta is equal to 36.87. And what that means, we know that cos theta is equal to, what is it, 4 over 5? And sine theta is equal to 3 over 5. So plugging those into this equation, we can get an answer for A in terms of the acceleration due to gravity. And what we'll get is A is equal to 2 times g times the cosine of theta. Cos theta is 4 over 5, so 4 over 5 here, divided by 9 plus 4 times sine theta, which is 3 over 5. If you don't believe me, you can plug these into your calculator. It's a 3, 4, 5 triangle that has an angle like this. So I believe what we got out of this, did this yesterday. I don't remember the answer, but this was 8 in the numerator, so it's 8g divided by, it's going to be 5 times 9, which is 45, plus, wait a minute, multiply 5, so it's 12. I feel like this is a different answer than we got yesterday. Maybe I made a mistake last time. It's basically going to be 8 over 8g divided by 45 plus 12. And 45 plus 12 is what? 59? No, 57? I'll have to go look back at the video from yesterday and see if I got a different number. I feel like I did, maybe. I probably just made a mistake somewhere. I could have made a mistake here, too. It was 2 plus sine theta. We squared it. There's the 4, and then the cross term is 2. Yeah, no, that looks right to me. Maybe this is the same answer I got yesterday. I don't really remember. So, but that would be the acceleration. It's approximately, because 56 is it's almost g over 7. Okay, that's the end. Do you guys have questions? There's the whole derivation. I included a lot more lines than you need. You can technically do this in, like, we could have gone from this line straight to the answer, but I'm sure that you guys would have missed some things. You guys have any questions? I'm gonna go ahead and stop the recording because our buddy that's making some background noise is back.